notations from the paper to the talk for simplicity reasons. So if you read the paper, don't be confused by the different notations. Just in the talk, it's somewhat simpler. And of course, if you have any questions or something unclear during the talk, please stop me. I will not go too much into details. There are quite a lot of details in the work. I will try to focus on the main ideas mostly. I'm sorry if somebody feels disappointed. You always can read the paper. Okay. So what we're going to talk about, first we will state the problem we're trying to solve. We will list some previous known results and then our result. Then we will briefly introduce tropical geometry, namely tropical hypersurfaces, which is a part of tropical geometry we will need. And then really briefly talk about the strategy of the proof. There I will really omit a lot of details, just give the impression mostly of the proof. Okay, so what is the setup that we're working in? So we're working in projective n space. So I remind you that it is a set of points with n+1 coordinates, not all 0, and we identified points that differ by multiplication by a non-zero scalar. Degree D hypersurface is a zero set of some non-zero homogeneous degree D polynomial in n+1 variables. And we will not, actually in our case, all the polynomials will be irreducible and clearly will not have repeated factors. So we have no kind of problems with non-reduced schemes or something like that. So we can identify hypersurfaces with the defining polynomials up to multiplicative constants. So this, of course, makes the space of hypersurfaces a projective space of the correct dimension that is written here, just by taking the coefficients of the polynomial as coordinates. And I call a one-dimensional linear subspace of this projective space a pencil, or sometimes a pencil of hypersurfaces. Okay, so a pencil is a one-dimensional object, pencil, and so the title is about singular hypersurfaces. What is a singular point of a hypersurface? Is a point where all the derivatives of the defining polynomial vanish. Okay, and of course this point has to be on the hypersurface, which actually follows from all the derivatives vanish in the projective case. But it's a point on the hypersurface where all the derivatives vanish. Okay, so this is a setup. What is the problems that we have to solve? So it's an enumerative problem. We're trying to count something. And what we want to, in the uninodal problem, we want to count the number of singular degree D hypersurfaces in a generic pencil. Okay, so I explained the words. So pencil, I said what it is. A generic means that I'm looking in open dense subset, open set subset in the space of pencils, which is a Grassmannian for who knows what it is. Or if you want, I'm looking for a solution that if I change a little bit the pencil, change a little bit, the solution will be still valid. And a singular hypersurface, of course, is a hypersurface having some singular point. And for dimensional reasons, since having a singularity is a co-dimension one condition, the singular points that we will have will be nodes. For those of you that know what nodes are, that's what we get, which are the simplest singular points that's possible. And again, for dimensional reasons, and since we pick a generic pencil, we will get a finite number of such points. So if we take a co-dimension one condition in a dimension one family, we get a dimension 0 solution, which is a finite solution. Okay. And we can generalize this problem to the multinodal enumerative problem, where we fix some natural number delta, and we count the number of degree D hypersurfaces in some generic dimension delta linear space, having delta singular points. And again, all the singular points will be knowns in this case for dimensional reasons. Okay, so this is the question. And of course, the question is highly dependent on the base field. So first we will.
Sorry, Uriel, can you
yes,
maybe say a couple of words of what nodal means?
Yes, so nodal just means that locally around the singularity, it's given by a non-degenerate quadratic form.
So the singularity is a point or a divisor?
It will be a point.
Mm-hmm.
It will always be a point. Okay. So when we walk over the complex numbers, as usual for the complex numbers, the solution does not depend on the particular choice of parameters as long as the choice is generic. And for the unionodal case, the result is classically known, and I believe known for a large part of the audience. It's the degree of the discriminant. The set of all the singular hypersurfaces is called the discriminant, and its degree is n plus 1 times d minus 1 to the power of n. For the multinodal problem over the complex numbers, the solution is also known. Maybe less so, but known, and it is equal to the degree of the discriminant to the power delta divided by delta factorial, and plus some small correction term. So the degree of this is d to the power of n delta, and this, of course, is smaller.
Uriel, when you say the result is classically known, you mean that this is the number of hypersurfaces of degree d with at least
with singularity.
With
because you can think about.
I
so
see.
you
Okay.
have. Yeah, so discriminant is a hypersurface inside the space of hypersurfaces, and when you intersect it with a line, you exactly count its degree. Okay, so this is a definition of the degree in a sense. Okay, any other questions? Great, so I continue. And I want to answer the question over the real numbers. And as usual, when we remove the algebraic closeness of the field, everything goes horribly wrong. So first of all, the solution does depend on the choice of the cutting subspace, even if we look at open subsets of in the parameter space. Okay, so this is a phenomenon that I believe all of you know, that if we take a polynomial of some fixed degree, it has always the same number of complex roots if we count, if we pick the coefficient generically, but over the real numbers, this is not longer the case. So this is nothing surprising here. So the question, as I stated it 2 slides ago, is meaningless. What we need to adapt it, and the way we decided to adapt it is we're looking for a cutting subspace that contain as much as possible a singular hypersurface. So this number is not constant, but we're trying to get as much as possible. And when I say as much as possible, it means we try to get as highest number as we can. We didn't prove it's the maximal possible, and it's probably isn't. Okay. So how can we restate this? So first of all, the way we choose cutting subspaces is by requiring the hypersurfaces to pass through some points. Passing through a point is a linear condition on the coefficients of the polynomial. So if we take sufficiently many such points, we get a linear space of the correct dimension. And this is the number of points we need to take to get a linear space of dimension delta. Okay, so the space of all hypersurfaces passing through those points is a delta dimensional linear space. And we denote as such the number of degree d hypersurfaces that pass through those points and have delta nodes, delta real nodes. Okay, so I'm looking for real hypersurfaces and having real nodes, no conjugate pairs of singular points or something like that. That doesn't interest me. And if we omit the P from the notation, we mean the supremum over all generic choices of P. Okay, so in a sense, the problem that I'm trying to solve is to bound from below this number. Okay, so this is a question. What are the known answers? So first of all, it is customary to mention Michalkin's paper from 2003, where he introduced a tropical approach to enumerative algebraic geometry. He wasn't dealing with this particular question, quite similar question, but not this one. But he did enough to mention him. So what about the particular question we at hand? So Bertrand showed that for curves in projective plane, you can get exactly the degree of the discriminant. So you can find an arrangement of points in the projective plane such that all the singular degree D curves passing through them, or the complex singular degree D curves passing through them, are actually real and have real singularity. As this is for the uninodal problem. For the multinodal problem, you can get something similar. The highest term you can get the highest term of the discriminant using the same techniques. Okay. Now, what happens in dimension higher, in dimension 3? So for surfaces inside a three-dimensional space, the uninodal case was studied by Markwig, and Shustin in 2017, and they found 1.5 times d to the third hypersurfaces in a pencil. And later, together with Christine Shaw, they generalized this to the multinodal problem. And you see that this is generalization. You have the same coefficients, the same result to the power of delta divided by delta factor. Another,
I
yes.
have a question.
Yes.
So in this O notation, does the implicit constant depend on delta, or it's universal?
Yeah, I believe it. Yeah, I believe it depends on delta. It should depend on delta. Yeah, I never vary delta. I don't think about delta as varying. That is always yes. For me, it just means this is a polynomial of degree 2, and this is a polynomial of degree 3 delta minus 1 in D. A polynomial in D in degree 3 delta minus 1. Okay, and in higher dimensions, the only solution that I know is a solution for the uninodal problem. And it also presented in the same paper, although it doesn't use any tropical geometry. It's an elementary construction. You just provide a polynomial by some degeneration. It's very elementary. And you can get roughly 2 times d to the n singular hypersurfaces. But again, this is only works for the uninodal problems. This cannot be generalized to the multinodal problem. And also, we will see that the coefficient 2 is not so good. You can get better. Okay. So what have we found?
Uriel, can you go back one slide, please?
Yes.
So am I missing something? But what happens if you plug in d equals 3 in the later result? Doesn't it improve on the...
I think you should take d high enough. I actually didn't think about smaller values for d here.
No, so not d, but rather n. If you plug in n equals 3, it seems that it improves the result
better.
of...
Yes, it is better. It is better, but only for the uninodal case. Yes, you're correct. In this case, the elementary construction is better than the uninodal case.
And what about upper bounds?
We don't know anything except the degree of the discriminant.
Okay, thanks.
Just I don't familiar with any works in this area.
Okay, thanks.
Okay. Any other questions? Great. So what I've showed is that we can actually get omega of d to the power of n for any dimension n, and I provided also the coefficient. So for some coefficients alpha n, you can get a solution for the uninodal problem equals to alpha n times d to the n. And for some another coefficients gamma n, you can get a solution for every delta solution for the multinodal problem equal to gamma n times d to the n to the power delta divided by delta factor. Okay, and I provided some recurrence relations for alpha n and gamma n.
So in the first result, the improvement is that alpha n is smaller than 2, or is there more improvement? I'm just trying to.
So first of all, the alpha n is bigger than 2, indeed. Yes, this is the improvement. Yes.
Thank you.
Yes, and alpha n and gamma n can be given by recurrence relation, which is appearing in the paper and not insightful enough and a little bit complicated enough to present it here. Just I decided to omit it, but I will give some numerical values. So for surfaces in three-dimensional space, alpha 3 is equals to 2.5, which is bigger than 2. So it improves on previous results. And also gamma 3 is equals to 5/3, which is bigger than 1.5, which is Markwig, Schoen-Schustin's result. So it improves on it as well. For large values of n, alpha n and gamma n tends to a constant. I didn't prove it or calculated the constant. I only provided lower and upper bounds. So alpha n, I'm sorry for the noise, alpha n is at least 4 for all n bigger than 14. It's bounded from above by 5, if it's interesting anyone. And gamma n is between 2.5 and 3, at least from some starting from some point. Okay, and again, the full details appear in the paper. And just to mention that, as far as I know, this is the first known result for multinodal problem in dimension larger than 3. Okay, so this is the result. We want to, I will briefly introduce tropical hypersurfaces. For that, we need the tropical semifield. The tropical semifield can be thought about what we want to be the codomain of a non-Archimedean valuation. Okay, we want to use some non-Archimedean valuations in our proof. So what is the codomain of non-Archimedean valuations? A non-Archimedean valuation turns addition to maximum and multiplication to addition. So we just pick the real numbers together with minus infinity. We will understand why it's minus infinity and not plus infinity in a second. And why it's a maximum and not minimum in a second. So we take the real numbers together with minus infinity, and we define tropical addition to be maximum and tropical multiplication to be the usual addition of real numbers. And this possesses all the properties of a field except having an additive inverses. So such an algebraic structure called semifield. And the additive neutral element is minus infinity because taking maximum with minus infinity doesn't change anything. And the multiplicative neutral element is, of course, 0. And a tropical polynomial is just the same as the classical polynomial, but with coefficients in the tropical semifield. So it's a finite sum of monomials with tropical coefficients, where I write the sum as a tropical addition and the multiplication as a tropical multiplication. And the degree of a polynomial is again the same thing that the degree of a classical polynomial, nothing new here. Okay. Now we want to do geometry, we want to draw some beautiful pictures. So we will need to associate to a polynomial hypersurface, some geometric object, which will be the tropical hypersurface. Unfortunately, here the approach of defining the zero, the vanishing set of a polynomial doesn't work because the vanishing set of a polynomial is not a meaningful thing here. If we take vanishing as equal to minus infinity, it's just the empty set almost always, and equal to 0, it's not interesting because 0 is not an interesting number here, it's not the additive neutral element. So what we do is something different. We look at the function defined by this polynomial. So we think about it as like a maximum of, and remember that multiplication is just addition, so here is written just some non-homogeneous linear form. Okay, so we look at maximum of such non-homogeneous linear forms, and we look at the corner locus of this function. What is a corner locus? Is the points where this function is non-differentiable. Okay, where it happens exactly where at least two of these non-homogeneous linear forms attain the maximum together. Okay, so we look at all those points. Let's see an example. So a tropical line, it's a tropical hypersurface defined by a linear polynomial. By this, for example, linear polynomial, 0 tropical addition x1, tropical addition x2, which is the maximum of 0, x1, and x2. And we look where this attains the max, at least two terms here attain the maximum. So if the coordinates are x1 here and x2 here, then, for example, at this ray here, x1 equals to x2 and greater or equal to 0. So both of them attain the maximum. And similarly for all other rays. And those rays continue to infinity. Okay. And the tropical hypersurface is always a polyhedral complex, and actually have some more properties. It's a balanced polyhedral complex, but I will not go into those details. Now, the main tool we use to study tropical hypersurfaces is by the dual subdivision. So what is a dual subdivision? If we take the Newton polytope of the defining polynomial, and I remind you that the Newton polytope is a convex hull of the exponents where, so classically there will be here, the coefficients are not 0, and tropically the coefficients are not minus infinity. So for the Newton polytope, there exists a subdivision into lattice polytopes, such that the cells of the tropical hypersurface correspond bijectively and inclusion reversing to all the cells of the subdivision except the points, except the vertices, so all the positive dimensional cells. Okay, so let's see an example. For example, I wrote some polynomial here, and I wrote the coefficients also on the vertices of the Newton polytope. So the 2 here is a coefficients of 0, 0, and for example, the 3 here is a coefficients of 1 and 1, so this coefficient. And here the hypersurface defined by this equation. So for example, this 4-valent vertex here correspond to this parallelogram here. Okay, and this 3-valent vertex here correspond to this triangle here, and the edge connecting them correspond to this edge between those two polytopes. And the points of the subdivision are not correspond to anything. In the hypersurface, they correspond to connecting components of the complement. Okay, so they also have some correspondence, and we use this, but it's not in the hypersurface. And this is very, very useful. We took our problem and changed it to problem in combinatorics, in something in lattice polytope, something that is studied. I don't know if quite well studied. We will see that there are some gaps that we would wish that would be filled, but so we can use some combinatorial tools, and this is very nice. Okay, how all this combinatorics and tropical geometry can help us solve our algebraic problem. So for that we need the non-Archimedean valuation, but our problem was in real numbers. We don't possess any non-Archimedean valuation of the real numbers. So we need to change the base field. Fortunately, we have model theory that can help us. And in model theory, there is a result called the Tarski transfer principle that says that the first order theory of real closed field is complete, is the same for every real closed field. And of course, our enumerative question can be formulated in first order theory, in first order logic, so we can change to another real closed field. For example, the Pizot series with real coefficients, which is a real closed field indeed. So if somebody wants me to remind what Pizot series are, this is a good place. Okay, great. So, and of course, Pizot series has the non-Archimedean valuation, which gives the lowest exponent with non-vanishing coefficient. Okay. Great. So now we can apply the theory of tropicalization, the theory that connects the algebraic case with the tropical case, and how it is done. So for a point where all the for a point that all the coordinates are non-vanishing, we can apply the negative of the valuation. So this negative is why is minus infinity and not infinity.
So Uriel, I'm a bit confused. K,
yes.
What K stands for?
Yeah, K is the Pizot series.
So it's a real closed field.
Yeah,
with a non-Archimedean valuation.
Yes.
What happens if you take the ultra product of R? I mean, then you get an extension of the ordered integration, no? Never mind.
I'm not familiar with
Forget
that.
about it. Yeah.
Okay.
No, it was not my question. So, just what is K? That was my question. Okay.
Yeah, it doesn't matter which. So what's happening in this slide is correct for any field with non-Archimedean valuation. Okay, so here K is some field with non-Archimedean valuation. Yeah, so I take points with all the coordinates non-vanishing, and I apply the minus of the valuation, and this minus sign is why we have minus infinity and not infinity, and why we have a maximum and not minimum in the definition of a tropical semifield. There are definitions with minimum, so as a min plus algebra and not max plus algebra, but then the correspondence to dual subdivision is confusing for me, and that, Leo, can you mute, please?
I didn't, sorry.
Yeah, and that's why I use this minus, because the correspondence to the dual subdivision is better, and also because the power of habit, and I'm used to it, so I'm very sorry for this minus sign. We will have to carry it around. So for such a point, I can apply the minus evaluation to all the coordinates and get a point in Rn. I can also tropicalize a polynomial. I take some classical polynomial just and apply the minus evaluation to all of its coefficients. And there is a theorem in tropical geometry called the Kapranov theorem, which is the particular case of the fundamental theorem of tropical geometry, which states that if we take a polynomial f and we apply the tropicalization to the polynomial and then look at the tropical hypersurface defined by it, or at the non-differentiability locus, or if we take this same polynomial, look at the vanishing locus of it inside inside Kn. This is inside the torus. And then tropicalize pointwise this set, we don't get exactly the same, but we get something that sits inside the tropical hypersurface and dense in it. So if we take the closure in the usual Euclidean topology on Rn, we get the same thing. Okay, and just maybe a remark here that here we use that the valuation is dense. The image of the valuation is dense in R. If we use some discrete valuation, for example, this is no longer the case, so some adaptation need to be done. They can be done for our problem, for example. We can use those results to get something for the discrete valuation.
Uriel, can you go back to the definition of KR?
Yes.
So I'm a bit confused. Okay, sorry.
Can you
I
explain
was
the
just
confusion?
confused. No,
Okay.
no, now it's okay. Sorry.
Okay. Yes.
Uriel, just a small,
yes.
Small question. The closure is Zariski closure or?
No, Euclidean. This
Euclidean.
sits in the Rn. Yes, because everything is polyhedral complexes, so we can use Euclidean geometry here quite well.
Okay, thanks.
Yes, and so maybe another remark. Maybe some of you noticed that I passed to looking at a problem at the torus. So originally my problem was in the projective space, and now on the projective space it doesn't really meaningful what I written here. We can define tropicalization of the projective space as well. We use a minus infinity there, but I decided for the talk it will be better not to do that. And it's not important. Why? Because we're looking at some generic pencil or generic delta dimensional linear space. All the interesting points, namely the point conditions and the singular points of all the singular hypersurfaces, would lie outside of the coordinates hyperplane, just because of genericity. So we can safely work with the big torus inside instead of the projective plane, and that's what we will do. Okay, just for simplicity, again, it's possible to do everything projectively, and in the paper I do more so, maybe not to the full extent, but more. But here I decided it will only confuse. Okay. So now we understood what a tropicalization is, how we can move our question from the classical world to the tropical world. But then we need to understand what happens to a singularity. Yes, we're interested in singularities in the classical world. So what happens to singularities in the tropical world? So the definition is just what we want. Okay, we just define it. Everything that comes from a singularity is called a singularity. Namely, a point on a tropical hypersurface is called singular. If exists some classical hypersurface and the singular point on it, Q, that tropicalized to this point psi, and the classical hypersurface tropicalized to the tropical hypersurface. And here I wrote them in other direction, but it's not important. It's just by Kaplanov theorem. Okay, so I define it just to be what I want, but it's not very useful definition because I don't have any way to check if a point is a singular, if a tropical point is a singular or not. Luckily, I do have a criterion, a combinatorial criterion for the singularity, and this is much of the strength of this approach for this problem. Namely the following. So if I have a tropical hypersurface defined by some tropical polynomial, for some real number, which will be height, I denote by FC all the x where the coefficients of the tropical polynomial is exactly equals to C. Then the point 0, which is a point where all the coordinates are 0, is in S and singular, so it's a singular point of S, if and only if, two conditions actually. So the points with the highest value with highest coefficient are affinely dependent. And I remind what an affine dependent in a minute, are affinely dependent. And for every height below the highest, maybe I need to write, so it's below the highest, there exists an affine combination of all the exponents with this coefficient that lie inside the affine hull of all the exponents with higher coefficients. And I remind you that the affine combination is a linear combination where the sum of coefficients is 1, and the affine hull is just a set of all such combinations of some set. And affine dependency is a linear dependency where the sum of coefficients is 0. So it's meaning that one of the members of the set is the affine combination of the rest. Okay. I will give examples in a second, but first I will just remark that here I give a condition for 0 to be singular for this point with all coordinates 0, but I said that 0 is not important, it's not an important point in any case, and it doesn't. By shifting the hypersurface just by adding some constant vector to all its points, which amounts to adding a linear functional to the coefficients, I can write the condition for any point to be singular. So 0 is not important, just the condition is a little bit nicer here, but it's not important. Okay, so examples. So the tropical curve from before is actually singular, and they actually have singularity at the origin, at the 0. So how can we see that? So the points with the highest coefficients, it's actually exactly this parallelogram, are affinely dependent. Okay, the sum of those two equals the sum of those two. And every other point is, of course, an affine combination of those. Okay, so it has a singularity at the origin. And also note that this origin is this 4-valent vertex, and this is not a coincidence. So always a 4-valent vertex in the tropical curve will be singular, and also a 5-valent, etc. Every valency higher than 3. And 3 is a typical case. So there is no 2-valent vertices at all, and 1-valent vertices are only at infinity in a sense. And we removed them, but yeah. Okay, so you can see that in a sense we can see the singularity in the picture, which is nice. Another example where it's a little bit harder to see this singularity in the picture, but it's possible, is this example. And here again, you can see the coefficients, the exponents with highest coefficients are affinely dependent. 3 points in a row are affinely dependent. The next level is those 4s, and they have an affine combination which lie here on this line. So it lines the affine hull of all the exponents with higher coefficients. And all the rest are in the affine hull, just in the affine hull of those points. So everything works. But now the singular point, it's not even a vertex of the curve. So I wrote here a point, but it's not a vertex. It's just the notation for this singular point. And it's the midpoint of this edge. And how can we maybe see that it's a singularity? So we can assign to all the edges, we can assign a weight. And the weight is the lattice volume of the corresponding cell in the subdivision. So the corresponding cell of this to this edge is this edge with the highest coefficients. Its lattice volume is 2, and we get here 2. And apparently, the midpoint of edges of weight 2 are always singular, of bounded edges of weight 2. Yeah, always singular. Okay, so it's not full characterization. It's actually so those two cases is the full characterization of what is called the maximal dimensional singularities. But we can get more complicated singular curves, and for higher dimension, of course, we can get even more. But those are some examples. Okay. Now we can use the lemma to give a definition, and this is maybe the central definition. So since we are looking at everything is generic, we can ask the affine combination in the lemma to be unique. Okay, and then we get the definition of graded circuit. So first recall what a circuit is. A circuit is an affinely dependent set of Zn whose every proper subset is affinely independent. And this means that there is only one affine dependency up to a scalar. So a graded circuit is a sequence of subsets, where the first is a circuit, and every next one has a unique affine combination that lie in the affine hull of all the previous ones with non-zero coefficients. Okay, so all the coefficients should be non-zero, and this is I think an intuitive definition following the lemma. And I view this definition as my main contribution, although it's quite immediate. The lemma, although wasn't written down as it is, it was known, but this definition and the focus on looking on graded circuits helped me a lot in the work. So previously, people looked more on the first level and look at circuits, not graded circuits, and then look at what singular points can be in such a hypersurface. But this approach has many disadvantages, and passing to looking at graded circuits, it was actually the main I think things that made this work possible. Okay. So examples in 2 dimensions. So we have just the examples of circuits. So a parallelogram is a circuit, and a triangle with interior point is a circuit, and actually up to a unimodular transformation, so a transformation with determinant 1 and integer coefficients. Those are the only ones, the only 2-dimensional ones. And we can also get a graded circuit by a 1-dimensional circuit, and then in the next level also some 2 points. Okay, so I put them here. In low dimensions, graded circuits were essentially, without this language of graded circuits, but were essentially classified by Marquardt, and Schustein up to unimodular transformations for all dimension up to 3. With additional requirements that they admit some convex function, which are the only ones that can appear in our case. Maybe I will say about the classification. So I said that in 1 there is only one such guy, in 2 there's 2 circuits, and also so what I showed in previous slides is essentially all of them. And in 3 there are actually an infinite family of circuits even. And in higher dimensions, such a classification is not possible. Because even the much more easier classification of empty lattice simplices, even only in dimension 4, was finished only in 2018 by Valino and Santos, Iglesias, Valino and Santos. And in higher dimensions, or if we want to pass to circuits, or if we want to pass to graded circuits, this is all much harder problems. So we cannot use such tools. And so originally, this is what we wanted to do. We wanted to just take the approach they used here, where they classified them, and using these classifications, they enumerated them, and just use this to come up with such classification in dimension 4 and enumerate. Originally, we wanted only dimension 4. We didn't think we could do something in higher dimensions. But then we understood that classifying it's very hard, and something else is needed, and that's what we did. Okay, so those are the main ingredients that go in the proof, and in the rest, in the remaining 3 minutes and some maybe minutes that I will steal from you, I will shortly outline the proof. So we start with some collection of points in the algebraic space, okay, in the big terms. We will choose those points later, but we should remember that this is a static position, and we denote by saying alg dp the set of all degree d singular hypersurfaces that pass through those points. We want to tropicalize, so we tropicalize all the points and pass to the tropical world, and we denote by saying tr the set of degree d singular tropical hypersurfaces that pass through. And it's obvious by the definitions that it took that tropicalizing a singular algebraic hypersurface get us a singular tropical hypersurface through those points. So the inclusion, so we want to enumerate this and say what's the size of this, and instead we will enumerate this. So as this is outlined for the uninodal problem, the multinodal is very similar but with more details. So we will enumerate this instead, and then from this understand this. Actually now equality here, but it doesn't really matter. And what will be important is that every guy here has a lot of preimages here, so it's not one-to-one. It's very not one-to-one. It's actually dependent on the degree, how many to one it is. So we enumerate this. And to enumerate this, we would like to use some classification of graded circuits, but there is not any such classification. So to overcome this, we put the points P, we put the points high, the tropical points, in some special position called Michalkin position. Okay, this is not invented by me. It's invented essentially by Michalkin. So these conditions on P, yes, we want the evaluation of the coordinates of P to be such and such. And this I will only say maybe a word about this Michalkin position. This, in a sense, we want to stretch the points very far one from each other. Okay, so we put the first points quite close, but the next one far, and the one after that a lot farther from before, and etc. So, and this makes the tropical hypersurface to be what is called floor decomposed. It has some nice structure that we can work with, and in this structure we can enumerate all the graded circuits that are. And for that we need to enumerate not only the tropical hypersurfaces, but the pairs tropical hypersurface with tropical singular point. Because this map from here to here is many to one, a tropical hypersurface in this scenario can have many tropical singularities coming from different classical singular hypersurfaces. Okay, so different classical hypersurfaces tropicalize to the same tropical hypersurface, but their singularities tropicalize to different points. Okay, and this is one of the challenges that was before. Before people enumerate only the hypersurface and then looked for singular points in it. And I do it together, and it's in a sense easier. Okay, and then we need to return to the classical world. This is done by some technique called patchworking, presented by Oleg Viro. Which is, in a sense, Hensel lemma. Okay, and doing this technique, we get two types of equations. We get systems of equations that have a non-degenerate Jacobian at t equals 0, where t is the parameter of the Pizot series, and then we can just get unique solution by Hensel lemma. And another type of equations that we get is a quadratic equation, which is essentially taking a square root. And there, if we work over the complex numbers, we have no problem, we can get two solutions. But if we work over the real numbers, we need to make sure that the discriminant is positive. And to make sure the discriminant is positive, we need to play with the signs of the coordinates of our points. And it's a delicate process because every coordinate goes into a lot of equations, and we need to make sure as much as possible discriminants are positive. here we will do like some kind of puzzle, and we presented some schemes for signs that get some discriminant positive, but we are sure there are some better schemes, but the paper was long enough, so we stopped there. And after that, if we count, we just need to do some combinatorics and count how many solutions we get. We get some recursive relation, and that's how we get the theorem. I think I skip the next two slides and finish here.
Thank you very much. So now we are